Good afternoon to all. I am Kajal from BSc Chemistry Honors final year. In today's session, I have prepared an audio lecture for visually impaired student from Inorganic Chemistry Volume 3rd, whose author Dr. BHASIN. So now let us start. Hard acid and soft acid and bases. The term acid and base are routinely used in our daily life. Chemist has been classifying substances as acid and bases since long time. Lavoisier notes that the common element in all acid was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy shows later that all acid contain hydrogen. It was in 1884 Archias, a sandwich chemist, developed the theory of acid and bases, known today popularly known as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance whose give hydrogen ions H positive in aqueous solution, and a base is a substance which give hydroxyl ion, it means OH negative in aqueous solution. The strength of an acid or a base depends upon its capacity to provide H positive or OH negative ion respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative equilibrium H2O. In 1923, J.N. Brosted in Denmark and T.M. Lawley in Great Britain independently possessed a acid-base theory. According to this theory, an acid is a proton donor, whereas base is a proton acceptor. The acid-base reaction, that is the neutralization, is regarded as a proton transfer reaction. In 1923, Jean Lewis gave another general definition of acid and base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor while a base is an electron pair donor. The earlier definition of an acids and bases are solely based upon the observable properties such as taste, ability to dissolve substance insoluble in water, and their effects on vegetable dyes. The term acid was applied to substances that have a sharp or sour taste, turn blue litmus to red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substance insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste, soapy feel, turn red litmus to blue. However, tasting and feeling chemical are dangerous method of determining whether the substance is an acid or a base. You should never ever taste or touch solution of chemical in laboratory. There are, however, another method of recognizing acids and bases. For example, acids and bases change the color of certain dyes, popularly known as indicators. On the one of the most common indicator is a vegetable dye obtained from the lichen known as litmus. Aqueous solution of acid turn the litmus red, whereas aqueous solution of bases turn it blue. Thus, any substances which has an unpaired pair of electrons can act as Lewis base, whereas a substance which has an empty orbital to accommodate a pair of electrons act as Lewis acids. In other words, substances capable of donating a pair of electrons are regarded as Lewis base, and the substances are capable of accepting a pair of electrons are regarded as Lewis acids. Acid base or neutralization reaction may thus be regarded as donor. It means Lewis base acceptor Lewis acid reaction to coordinate covalent bond formation reaction. The classical example of a Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and the ammonia is the Lewis base. NH3 plus BF3 is equal to NH3, its lone pair gives to BF3. Donor acceptor or coordinate bond formation reaction. Lewis acids of acid and bases is very commonly used because of its simplicity and the ease with which the formation of the coordinate compound can be explained. In brief, all the usual ligands can be regarded as Lewis base, whereas all the metal ions can be regarded as Lewis acids. The degree of affinity of metal ion for ligands can be termed as Lewis acidity, and the tendency of the ligands to combine with the metal ion can be regarded as the Lewis basicity. Hard and soft acid and bases. An acid-base reaction, according to the Lewis concept, involves the reaction between a donor and an acceptor to form a complex, is as given that A plus B have lone pairs, which is equal to A lone pair to B. The formation of the stable complex between the donor and the acceptor depend upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with the metal ion, such as Ag positive, Ag2 positive, Pd2 positive, and Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, CO3 positive, and Pt4 positive. Based upon the preferential bonding, the acid and the bases has been classified into the two groups, class A and class B, according to their preferences. Class A metal ion includes alkali metals, alkaline earth metals, lighter and the more highly charged ion, for example, Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, and CO3 positive, etc. Hydrogen ion H positive. And in class B, metal ion involve higher transition metal of second and the third transition series, Cd2 positive, Hg2 positive, Pd2 positive, Pt2 positive. Higher transition metal in lower oxidation state, Ag positive, Hg22 positive, Cu positive. Low valent metal ions such as zero valent metal in metal carbonyls. Depending upon the type of metal ion, ligands can be classified as class A and B depending upon their preferences. Class A ligand involve molecule or ions with donor atom NOFCl, etc. It is important to note that class A ligands prefer to strong complexes with class A metals. Class B ligands involve molecules and ions with donor atom P, AS, S, SE, I, etc. Class B ligands prefer to form complexes with class V metal ion. It was in 1963 Pearson coins the term acid and bases for class A and class B metal ion ligands respectively. According class A metal ion are referred to hard acid while class B metal ion are referred as soft acid. Similarly, ligand are named as hard acid. Similarly, class A ligand are named as hard base whereas class B ligand are termed as soft base. In summary, according to Pearson, class A acid are hard acids such as H positive, Li positive, Na positive, Be2 positive, Mg2 positive, Cr3 positive, Fe3 positive, etc. Class B acids are soft acids such as Ag positive, Pd2 positive, Cu positive, Pt2 positive, etc. Class A bases are hard bases, that is H2O, NH3, F negative, and ROH, etc. Class B bases are soft bases such as R3P, R3AS, R2S, R2SE, I negative, SCN negative, etc. Classification of acids and bases as hard and soft. Pearson observed that it is possible to correlate acid base interaction on the basis of hard and the soft acids and bases. He observed that type A metal ion, that is acids, were small, compact, and not very polarizable, and these preferred ligands that were so small and less polarizable. He called these acids and bases as hard. On the other hand, type B metal ion and the ligand they prefer appear to be larger in size and more polarizable. He described these acids and bases are soft. Pearson generalized the acid-base relationship can be expressed that hard acid prefer hard bases and the soft acids prefer soft bases. Classification of acids. A general classification of some common hard and soft acids along with some borderline cases is given in that table. Next one, hard acids, cation of high oxidation. Hard acids are cations of higher oxidation state. For example, Cl3 positive, Cl7 positive, I5 positive, and I7 positive. Hard acid are molecules cations with lesser number of valence electrons. Hard acids hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acid bind stronger to a proton. Hard acid are small sized, compact, and are not easily polarized. As similarly, soft acid possessed the following characteristics such as soft acids are cation of larger size or heavier elements. Soft acids are cation of lower charge. Soft acids are molecules ions with large number of valence electrons. Soft acids do not hold the valence electron tightly and are therefore easily polarizable. In summary, soft acids are large sized and easily polarizable ions molecules that bind strongly to highly polarizable ion or molecule. It is important to note that there is no sharp division between the hard and the soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such type of acids that are neither hard nor soft are called borderline acids. Borderline acids have properties which are intermediate between that of a hard acid and a hard base. In case of borderline acids, the properties such as size, oxidation state, polarizability of cation molecule are neither too low nor too high. On the other hand, soft acids will show the opposite trends of the following order of the preference for binding the donor atoms ions within a group is observed. Classification of bases. A general classification of some commonly used ligands into hard acid into hard and soft bases along with the border lines are represented in the given table. At this table, some of the important characteristics of the hard bases. Hard bases bind strongly to the proton. Hard bases contain donor atom of high electronegativity. The donor atom in the hard bases possessed low polarizability. The hard bases are not easily oxidized. Hard bases contain empty orbital of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is of high electronegativity and of low polarizability. The further inspection of table 4.2 reveals that following features are observed in case of soft bases. Soft bases contain donor atom of low electronegativity. Soft bases contain donor atom of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative non-metals including C, S, P and I. The donor atom in such bases possess donor atoms that are easily polarized. Just as there borderline acids, there are borderline bases also. The property of borderline bases are in between those of the soft and the hard bases. It is important to note that the categories are not rigidly divided. For example, the halide ions forms a series from the very hard fluoride ions through the hard borderline chloride ion to the borderline bromide ion and the soft iodide ion. The soft acids, also known as class B metal ions, the group of the metal ions that are in the lower right portion of the metallic elements as shown in figure 4.1. Now, Pearson HSAB principle. Pearson proposed a simple rule for predicting the stability of coordination compounds formed between acids and bases. This rule is quite often named as HSAB principle. According to Pearson, HSAB principle is that hard acid prefers to bond with hard bases, while soft acids prefers to bond with soft bases. It is important to note that hardness and the softness of acids and bases refer only to hard and soft interaction. It is by no means related to the strength of acids and bases. For example, both F negative and OH negative ion are hard bases, while the basic strength of OH ion is approximately 10 raised to power 13 times that of F negative ions. In other words, hard acids will show the following order of the preference of bonding the donor atom ion within a group. Applications of HSAB principles. Pearson principle of HSAB has a number of applications in inorganic chemistry. Some of these are discussed below. Stability of complexes. We have already noted that the hardness and the softness of acids and bases are related only to the hard and the soft interaction. Hardness and softness of acid and bases has nothing to do with the inherent acidic or basic strength of the acids and bases. For example, both OH negative and F negative ions are hard bases, although OH negative ion is for stronger a base than F negative ion. In fact, OH negative ion is 10 raised to power 13 times more stronger a base than F negative ion. However, in HSAB principle, both OH negative and F negative ion are afar with each other. Pearson in 1963 explained the relative stability of coordination complexes on the basis of HSAB principle. Let us consider a general relation between Lewis acid and Lewis base. Lewis acid plus Lewis base is equal to their complexes. The complex AB will be most stable if A and B are either both hard and both soft. The complex AB will be least stable if A is hard and B is soft, or A is soft and B is hard. For example, a complex between soft acid Ag positive and soft base I negative ion is quite stable, in contrast to the one ion between a soft acid Ag positive and a hard base F negative. Similarly, the reaction between the LiI and CSF resulting in the formation of LiF and Si constitute an interesting example suggesting the preferential stability of the soft-soft and hard-hard combination. LiI is considered as hard-soft and CHF soft-hard, which is LiF, also known as hard-hard, and CSI is soft-soft. Now a question arises, why COF3 F6 bracket close 3 negative complexes is more stable than COI6 3 negative. In both complexes COF6 thrice negative and COI6 thrice negative, the oxidation state of cobalt is +3. CO3 positive is a hard acid. There is a combination with a hard base. F negative will lead to COF63 negative, which is hard interaction. On the other hand, combination of C3 CO3 positive with a soft base I negative will leads to COI63 negative, which is hard soft interaction. Thus COF6 is more stable than COI6. It has also been noted that the combination of hard and or soft ligands with the metal ions is always preferred over a combination of a mixture of hard and soft ligand with metal ion. For example, the complex of CO CN5I 3 negative and CONH35 F2 negative are far stable, whereas the complexes COCN3F thrice negative and CONH3 thrice I 3 positive are stable. This is because Cn negative and I negative are both soft, whereas NH3 and F negative are both hard bases. Classification of acid and bases. The acid and bases can be classified as hard or soft depending upon their preference for hard and soft reaction. Let us consider the following. BH positive plus CH3Hg positive reactions takes place in equilibrium. CH3HgB positive plus H positive. Similarly, the examples, we know H positive is a hard acid whereas CH3Hg positive is soft base. If B happen to be hard like NH3, the reaction on the left hand side will be preferred as given this. Similarly, this. Now the definition of hardness primarily uses the idea of polarizability, which states that less polarizable species is hard or a more easily polarized is soft. For ion of similar charges, the ratio of charges of radius should be used to access the relative polarizability. However, HSAB principle does not take into consideration the quantitative idea of relative hardness and the softness of the species. Major limitations of HSAB principle. HSAB principle is too general and without any qualitative scale of measurement. HSAB principle does not take into consideration of the acidic and the basic characteristic of the compounds. HSAB principle fails to explain the feasibility of the reaction. It is probably the greater acidity of the protons H positive relative to the CH3 positive cations that is responsible for the unfavorable reaction. Now the limitation of HSAB principle. The hardness and the softness of an acid or a base is primarily related to the stability of the hard and the soft interaction. It has no concern with the acidity and the basicity of the acid or the bases. For example, OH negative and F negative are well-known hard bases. However, the basicity of the hydroxide ion OH negative is very larger as compared to the fluoride ion. In fact, the basicity of hydroxide ion, which is approximately 10 raised to power 13 times that of fluoride ion. A strong acid is well known to display a weak acid. For example, the reaction between the sulfide ion and the hydrogen fluoride process in the forward reaction. It means that the stronger bases SO3 2 negative can easily replace the weaker base F negative ions from the acid hydrogen fluoride. SO3 2 negative plus HF, which is given to HSO3 negative and F negative. However, the above reaction is not favored according to HSAB. SO3 2 negative soft base plus HF hard, which is give HSO3 hard soft and F negative hard base, which is only favor hard and soft interaction. Similarly, this example. Now, symbiosis. The hardness or the softness of an acidic or basic center is an inherent property of an atom, but depend upon the substituent. The ammonia is hard base while the pyridine is a borderline base. The acidic B3 positive ion is borderline between a acid and a soft base. Addition of three small sized non-polarizable substituent like fluoride ion make it a hard Lewis acid, whereas addition of the electron donors and easily polarizable group like hydride ions make it soft Lewis acids BH3. The difference in the hardness and the softness of the BH3 and BF3 can be illustrated nicely in the following example. R2S dot BF3 plus R2O, which is given to R2O dot BF3 plus R2S. R2O BH3 plus R2S, which is given to R2S BH3 soft plus R2O. Hard ligands have the tendency to combine with the metal ion having hard ligand, and the soft ligand have tendency to combine with the metal ion already having soft ligand, are coined as the term symbiosis. An important outcome of the symbiosis, that is the symmetrical constituent compound, are formed in the preference of the unsymmetrical substituent compound. For example, compound containing mixed substituent interact strongly to yield symmetrically compound with the sum constituent given below this: BH3F negative plus BF3H negative, which is given to BH4 negative plus BF4 negative. Theoretical basis of the hard and the soft principle. First is electrostatic interaction theory. According to this theory, hard acid and hard bases form purely ionic compounds. Therefore, hard interaction are purely ionic or electrostatic. Most of the hard acids such as Li positive, Na positive, K positive, etc., and hard bases such as O2 negative, F negative, and OH negative are well known to form ionic compound. We know that electrostatic energy of an ion pair is inversely proportional to the interaction distance. It means smaller the ions, smaller will be the interaction distance, and hence greater will be the electrostatic energy between the ions. As a result, the finally compound formed by the hard acid and the hard bases will be highly stable. Second one, polarizing power and the polarizability. Electrostatic interaction cannot explain the soft interaction because of the bigger size of the ions, soft ions. Therefore, the interaction between the large sized acid and the bases must involve the covalent character. Soft acids such as Ag positive, Hg positive, Cu positive form the compounds with the soft bases like I negative, S2 negative, etc., which have substantial covalent character. Almost all the soft acids have 6 or more d electrons. Soft acids with D10 configuration are excellent soft acids. For example, Ag positive, Hg2 positive. It is these D electrons have more polarizing power. Secondly, the soft acid like S2 negative and I negative are easily polarizable. Bonding between the soft acid and soft bases is largely covalent. Third one is natural occurrence of ores and the minerals. Natural occurrence of the ores of the certain metals can be easily explained on the basis of HSAB principle. Hard acid metals such as Hg2 positive, Ca2 positive, Al3 positive, etc. occur as their oxide fluoride primarily due to their preferent acid and bases interaction. We know the oxide O2 negative Fe F negative Cl carbonates all are soft bases. These hard acid metal ion cannot occur as sulfide because S2 negative is a soft base and cannot form stable compound. Thank you so much.